Hello everyone, my name is Anggit Raksajati. In this video, I'm going to present you a preview of types of pumps and blowers in the Fluid Mechanics and Particle course. So, what is a function of pumps and blower? This equipment is used to supply the energy to enable a flow compensate the friction loss across the pipeline. Pump is used to compress a liquid, which is an incompressible fluid. Meanwhile, fan or blower is used to compress a gas, but only for a relatively small compression ratio, so it still could be considered as incompressible process. When we talk about incompressible process, that means the density will not change during the suction and the discharge of the compression process. By supplying the work into the pump or the blower, the energy will be converted to increase the pressure, velocity, and or the level of the fluid. This slide shows you some of the most commonly used equations to calculate a pump duty. Liquid is known as incompressible fluid, so the calculation is much simpler than the calculation of compressor duty explained in the thermodynamic course. As you can see, work is the integral of volume times the delta pressure, but because liquid is an incompressible fluid, that means the volume or the density doesn't change during the pressure difference between P1 to P2. So the calculation is simple. If you want to express it as head or in meter, as shown you at the left side equation in this video, the head of the pump can be calculated as the delta pressure divided by the gravity constant and the density. If you want to express it in power, that means in watt or kilowatt, it's shown in the middle part of this video. So you just have to times the head with the volumetric flow rate, the gravity constant, the density, and then divide it by the unit conversion. Then you get the hydraulic in kilowatt. The hydraulic means it's still considered as ideal reversible compression. Once you put into account the efficiency of the pump, so it's known as a brake power in kilowatt, for example, you have to divide the hydraulic power by the efficiency, so that's the actual power that has to be supplied. So this slide shows you two of the most commonly used pump. The first one is a centrifugal pump and the second one is a positive displacement pump or a PD pump. For the centrifugal pump, it is relatively cheap, low maintenance fee, and small in size. That's why it's very popular to be used in industry. The operation velocity typically around 1200 to 8000 RPM in terms of the impeller rotation. In some special case, a very high velocity can be used, for example up to 23,000 RPM, but only for a low capacity pump. It tends to achieve a higher head and operated at constant head and varying capacity, as will be explained later when we talk about the pump curve. The second type, for example, a reciprocating or a rotary pump, which is a type in PD pump, operated at constant capacity and varying head. It is suitable for a service that requires high and varying head. It is also suitable for injection, in some case methanol and corrosion inhibitors with constant capacity. This is a simple illustration of a centrifugal pump. It can be designed as a one-stage pump or even a multi-stage pump for a very high pressure, for example. And the design, and including the shape of the impeller, can be varied depending on the type of the fluid, the pressure requirement, and so on. But actually, it is studied much more detailed in mechanical engineering, not in chemical engineering. As a chemical engineer, our focus is on the performance of the process characteristic of the pump itself, like the pressure differential, and then the work required, the characteristic of the fluid, and so on. As you can see in this animation, the fluid going into the pump, and then it will receive energy from the rotation of the impeller. So the kinetic energy of the impeller converted into the kinetic energy of the fluid, and then later on the kinetic energy of the fluid is converted into potential energy, or the pressure, going into upward direction in this example. This is example of a centrifugal curve from a GPSA, or Gas Processor Suppliers Association. Let's say this is example for a depropanizer reflux pump with a very specific impeller diameter, in this case 292.1 millimeter. So there are a lot of things that can be gathered from this type of curve. For example, in the x-axis you get the flow rate in terms of cubic meter per hour incoming to the pump. In the y-axis you have the head generated by the pump in terms of meter, expressed in meters. And then there are a couple of lines and curve inside of the pump curve. For example, you have efficiency curve. So every point attached to this first curve has 68% efficiency. The outer curve, that's 67 efficiency, up until the outer curve at 50% efficiency. And then you also have, for example, 4 different kinds of impeller diameter. The smallest one is 215.9 up until 292.1 millimeter, depending on your needs for this specific pump series. So how to read this curve? For example, you have feed at 100 cubic meter per hour. That's a vertical line. And then let's say you use the highest impeller diameter at 292.1 millimeter. So that will give you around 150 meter of head generated. So if you have 10 meter as the suction head, the discharge head of this pump will be 160, 10 plus 150, and so on. And then you can match it with the curve. It intersects with 67% efficiency. But at different condition, you may have a different efficiency and different head as well. And then you can also get information about NPSH, or the net positive suction head, which will be explained in the next video. It is to determine a cavitation to prevent any vapor generated in the pump, so it will damage the pump. For example, for this pump series at 100 cubic meter per hour, the net positive suction head required by the pump is 3 meter. Below that, it will lead to cavitation. So the second type, the PD pump, we will talk about 2 main types of PD pump. The first one is a rotary pump. It moves the liquid by rotating gears inside the pump chamber. The second one, reciprocating, it moves the liquid by reducing internal volume of the pump by piston movement. So liquid comes out in high pressure. At this PD pump, the volume of liquid transported depends on the motion velocity, back and forth, as in piston, or rotating in rotary pump. PD pump works in a stable velocity. So this is an illustration of the rotary pump. As you can see, at least there will be 2 gears which moves or rotates at different direction. So when the fluid going into this pump chamber, because of the rotation of the gear, it will increase the kinetic energy of the fluid and can increase the pressure of the fluid. There are a couple of rotary pumps, so it can be as a lobe, it can be as a screw, as a vane, or as a gear. So this is the second type of PD pump, which is a reciprocating pump, where a certain volume of liquid is collected in enclosed volume and is discharged using pressure to the required application. Reciprocating pumps are more suitable for low volumes of flow at high pressure. So as you can see, when the piston moves to the left direction in this example, it will draw the liquid into the chamber. So it could be said as an expansion process because the volume increases. And then when the piston moves in the opposite direction, to the right direction, it will push the fluid going out of the enclosed system of the pump with a higher pressure because of the piston movement. So that's the end of this video. We will talk about it in detail in class. Thank you for listening.